Well, Mr. Johnson couldn't have been the killer.
And why's that, Watson?
Well, look at his ladder. It's longer than the barn the witnesses saw the masked culprit moving through, albeit at close to the speed of light.
The ladder may be longer in this reference frame, but you've forgotten the principle of Lorentz length contraction. If the culprit was moving at close to the speed of light, from the witness's perspective, the ladder would be smaller than the barn.
I thought of that. But the witnesses also saw the doors on both sides of the barn close as the ladder went through. Contradiction or not, from the culprit's perspective, the ladder wouldn't be smaller than the barn. How could both the doors close together if the ladder was longer than the barn?
Together, I see you've fallen into the paradox of simultaneity. At these speeds, what the witnesses saw as simultaneous events would be delayed for the culprit. The first door would open and the ladder would move in further, and then the back door would close. No more paradox. Therefore, since all other evidence points to Mr. Johnson, he must be the killer.
Yeah, and I would have gotten away with it too if it weren't for your vast knowledge of the invariance of the laws of physics and all inertial reference frames.
Well, Holmes, you've done it again. How do you do it?
Simply relativity, my dear Watson. Everything is connected. To learn anything, you have to build on what you already know. Whether it's science, art, or philosophy, we can connect everything to anything. So let's learn anything. Let's find those connections and let's build our intuition. Welcome to Intuition. I'm your host, Evan Noce, and what plane of existence do you live on? And I'm not talking about Earth, the material plane, or Middle Earth. I'm talking about plane in the mathematical sense. In geometry, a plane is a two-dimensional surface that extends indefinitely in all directions. And we use planes to analyze, well, just about everything. So, I ask again, what plane do you exist on? A rectangle? A sphere? A hyperbola? The answer isn't as obvious as you think. If you've ever heard of an XYZ coordinate system where you identify things at X, Y, and Z coordinates, you're actually using rectangular surfaces to analyze the world. This is known as a Cartesian coordinate system and has been the golden standard for representing three-dimensional space for hundreds of years. Cartesian coordinates are built on what's known as Euclidean geometry. Euclid was a Greek mathematician whose theories and proofs on geometric elements remain the foundation of modern mathematics. We will be condensing and combining it to a few key points. Number one, the shortest distance between 2 points is a straight line. Number two, two parallel lines always stay the same distance from each other. And three, the sum of any two angles in a triangle is less than two right angles, all of which may seem self-evident. Let's go ahead and test some of these. If you were to mark 2 points on the floor of a room and wanted to determine what path would be the shortest distance, you could take a tape measure and figure out that a straight line is the correct answer. Great, that's number one. Next, if you drew another line parallel to the first and extended them for as long as you want, they would stay the same distance from each other if you checked with a tape measure every step of the way. That was number two. Finally, try to draw a triangle with at least 2 right angles, and no cheating like the gardener did. It's impossible. So, maybe we live on a rectangular plane. That is what Euclidean geometry and Cartesian coordinate systems are based on, right? Well, no. The Earth is not rectangular. It's a sphere. The reason Euclid's propositions seem to work on Earth is purely a matter of scale. We are significantly smaller than the Earth. So let's see what happens when we try to do the same experiments on a sphere. If you have something round like a tennis ball or stress ball on hand, this is much easier. But if not, I'll try my best to help you visualize. Take a piece of paper and try your best to crumble it to the shape of the sphere. Mark 2 points on the sphere and make sure they aren't on the equator. Now, draw the shortest distance between those 2 points and take off the piece of paper. The resulting line will not be straight. On a sphere, the shortest distance is not a straight line. This is part of the reason planes appear to take a curved path. They are actually taking the shortest path, but when we flatten the Earth into a non-spherical plane, the shortest path is not a straight line anymore. Next, imagine putting 2 strips of tape around the ball parallel at the start. If you do not bend the tape, the once parallel lines will crash into one another at some point on the sphere. Parallel lines don't stay the same distance on a sphere. Finally, take your finger and place it on the equator of the ball. Run your finger directly north until you reach the top. Now take a right turn at a right angle and follow the path back down to the equator. Finally, take another right turn at a right angle and follow the equator back to where you started. You just made a triangle with 3 right angles. All 3 of our Euclidean statements were shown to be false on a sphere. So where does that leave us? Are we on a rectangle or a sphere? Well, neither again. You see, this tangent, see what I did there, has been intentional as the jumping off point for what I actually want to talk about. Einstein's relativity. Just like how we needed to change the scale on size to see the effects of living on a sphere had on our geometry, to understand relativity, we're going to have to start moving very fast or get very big. See, relativity is actually 2 separate theories that Einstein came up with: special relativity and general relativity. We will begin with special relativity. Special relativity has 2 postulates, or propositions like Euclid. Number 1, the laws of physics are the same in all inertial reference frames. Number 2, light travels in a vacuum with the same speed in any direction in all inertial reference frames. So let's break it down, starting with the first postulate. An inertial frame of reference. Sounds like a mouthful, but it essentially means this. No matter what angle we tackle a problem from, the resulting physics will yield the same solution. An example of this comes from our lesson on planes. We analyzed how wind would move over a static wing, which is the same as analyzing what happens when a wing moves through static air. Imagine a car driving by you as a pedestrian. From your point of view, or frame of reference, the car goes racing past you. If you were in the car, though, the car remains still as the pedestrian goes racing past you. Now let's think about something like gravity. Imagine you are in a sound and vibration isolated box on Earth. You would feel the acceleration due to gravity of 9.81 meters per second squared. Now imagine you were in a box that was strapped to a rocket accelerating at 9.81 meters per second squared. Would you notice the difference? Einstein says no. No reference frame gets special treatment. Good so far, right? Let's move to the second postulate. Light travels the same speed in any direction in all reference frames. What does that mean? This one's a bit harder as there aren't as many daily examples of this occurring for us to prove or disprove this. So instead, let's assume it's right and see where the logic takes us, kind of like what we did with the two horns argument from our ethics episode. Imagine a train with a mirror on it. A person with a flashlight stands in front of the mirror and turns it on and off. From the perspective of this person, the light would move at the speed of light to the mirror and then bounce off and move back at the same speed at the person. Fine so far. But now let's look at someone watching this from off the train. As the train whizzes by, the light is turned on. Normally, we would add the train's velocity to the speed of light. Like if you threw a baseball in the direction of the train, we would add the ball's velocity to the train's velocity to get the total velocity. But if light is the same speed in all reference frames, we wouldn't be able to do that. If we added the speed of light to the train's speed, then the light would be moving faster than the speed of light, which breaks the second part of special relativity and therefore can't happen. So what happens instead? The observer would see the light take more time to get to the mirror and then bounce back. Wait, what? That's impossible, right? I mean, the first postulate says the laws of physics are the same in every reference frame. So how could light appear to move differently in two different reference frames? The key word is appear. It turns out that when we mix time with space, we live not on a rectangle, not on a sphere, but a hyperbolic plane. Trust me, I wish it was simpler, but the fact of the matter is that space-time is not Euclidean. It's not Euclidean, and its effects are only noticeable once we change the scale. Now, hyperbolic plane sounds like something from a science fiction movie, so let's analyze that first. A hyperbola is the shape you get from the equation y equals 1 over x, which is kind of like two bowls that extend infinitely. The key concept to glean from this, though, is that hyperbola have something called an asymptote. What did you just call me? No, it's a math term. It means an asymptote is a line that a function will approach indefinitely but never cross. So, if we live on a hyperbolic plane, then there is an asymptote, something that we can get close to but never cross. The speed of light. Special relativity gives us insight into a sort of speed limit of the universe, something that nothing can go faster than. The upshot of this is that the universe will do everything in its power to prevent anything from going the speed of light, including changing the apparent flow of time and the length of objects. One of the tenets of special relativity is the idea that running clocks move slower, and from our train example, we can start to see what that means. In order for our observer to see the flashing light on the train move at the speed of light despite the additional speed of the train, two things could happen. One, time on the train could be moving slower. From the perspective of the person on the train, everything would be normal. But from the side observer's perspective, time would slow down on the train. Thus, from both perspectives, the event of the light bouncing off the mirror will never exceed the speed of light. In other words, in order for both parties to observe light moving at the speed of light, the time it takes for the event to happen must change based on the speed of the perspective viewing it. And this isn't an illusion either. If you were to take two watches and place one on the train and move it close to the speed of light, the watch on the train would be behind the one that wasn't. Confused yet? Let's confuse you even more. Not only does time dilate, but length contracts when you move close to the speed of light. Imagine you walked down the length of a train moving at relativistic speeds. From your perspective, the train would be the same length as it was at the station. But from a bystander, just like how time had to compensate for the speed of light, the measured length of the train would also shrink. The effect only occurs while you're moving, though. It's not a permanent alteration. Do you have stubborn fat that you can't get rid of? Try our new relativistic weight contraction program. Appear to melt away the pounds as you rev up to 0.7 C. Effects are only temporary. Relativistic weight contraction is not responsible for any false perceptions created by this program. Now, just like our sphere example, both of these effects are present for any moving object. It is only noticeable when we change the scale. Let's go ahead and take a break, and when we return, we'll move from special relativity to general relativity. All right, so what do you think? Pretty cool podcast, right? I guess the host isn't too annoying. I just don't understand his explanation of why moving objects move slower through time. Oh, well, that's easy. It's called time dilation, since space-time operates in non-Euclidean geometry when... Whoa, this is too much. Explain it to me like I'm 10. Light is always the same speed. In order for that to be true, someone moving relative to you must experience time at a slower rate. Explain it to me like I'm 5. Light always goes zoom, so if you go zoom, light also have to go zoom. Explain it to me like I'm French. Je ne peux pas parler le français. Explain it to me like it's Friday. Well, it's when... forget it. Explain it to me like it's Monday. Well, it's when... forget it. Explain it to me like it's New Year's. Light is always the same speed. In order for that to be true, someone moving relative to you must experience time at a slower rate. Also, Happy New Year's. Explain it to me like I'm explaining it to you. Explain it to me like, wait, what's happening? Explain it to me like you're telling me how to defuse a bomb. Okay, so now the light is going to be traveling the same speed for the moving clock and your clock. Do you see the moving clock? How did you explain it the first time? Light is always the same speed. In order for that to be true, someone moving relative to you must experience time at a slower rate. Oh, now it makes sense. Space-time exists on a hyperbolic plane, so as your reference frame moves, time has to slow down to compensate for the moving reference frame. Exactly. Welcome back. Before the break, we discussed special relativity and how physics bends to the speed limit of the universe, the speed of light. Now, we're going to move on to another form of relativity, general relativity. It's my opinion that general relativity will be easier to grasp than special relativity, especially since we have already laid the groundwork for non-Euclidean geometry. So, let's begin. I mentioned in the beginning that both forms of relativity are not readily observable from the scale we see on a daily basis. In special relativity, we needed to accelerate close to the speed of light, but in general relativity, we need to think bigger, literally. General relativity deals with how objects like planets and stars interact with one another through gravity. Now, if you've ever been alive, you've probably heard of gravity as a thing pulling you down to Earth. Yeah, man, he's like a super down-the-earth guy. Right, Jerry? Right. But why is gravity pulling you to Earth? If you remember from our lesson on forces, causing objects to accelerate is a form of work. So if you're constantly being pushed towards Earth, how is merely the presence of Earth causing you to accelerate? Are planets forms of free energy? First, there is no free energy, so something else must be at work. In a few ways, gravity is similar to magnetism. A magnet has a range of influence on the world around it called a magnetic field. Likewise, anything with mass has a gravitational field. Unfortunately, the similarities end there, as unlike how magnets have a positive and negative pole, there isn't any negative mass yet. But at least we can start to understand the influence mass has on the space around it. Now, we can pull in our understanding of special relativity to help us start to answer this question of what mass is doing to the space-time around it. Imagine a satellite high above Earth's surface, which, for the sake of argument, has a uniform gravitational field. This satellite has one job. It shoots a pulse of light towards Earth's surface. When the light reaches Earth, a small device captures that energy, then uses all of that to shoot a marble back up to the satellite. Once the marble reaches the satellite, it falls back down and transfers its kinetic energy to the satellite, starting the process over again. Light into momentum, momentum into light. First, in order for the conservation of energy to remain true, this loop cannot gain any additional energy. And since light does not technically have any mass, there must be a gain in energy as light accelerates to Earth. Sparing you from the derivation, this energy is the initial energy times the gravitational acceleration times the height to the satellite divided by its speed, which is the speed of light, squared. EGH divided by c squared, which might be easier if you're reading. This increase in energy must be equal to the potential energy gained from launching the marble to the same height, which is mass times gravitational acceleration times the height of the marble, mgh. Set those equal and cancel out similar terms, and you get the formula mass equals energy divided by the speed of light squared. E equals mc squared. Pretty cool, right? That's where the famous formula comes from. Pat yourself on the back if you made it this far. This is complex stuff, and it's no small feat to wrap your head around. In fact, it may take you multiple listens of this and previous episodes in order to fully grasp it. In fact, it's only until I am doing this physical podcast that I feel like I actually have an understanding of this stuff. But we aren't done yet. Remember that light can't move faster than the speed of light. So as it's in a gravitational field, when most things would start to speed up, light has to stay the same speed, and other things must compensate. Turns out speed isn't the only thing that can mess with time. Gravity can too. Gravitational time dilation occurs when objects exist within a gravitational field, and based on what we know about special relativity, that means space-time around anything with mass isn't flat. It's curved. Planets and suns and even ourselves are warping space-time purely by existing. And from our initial discussion on breaking non-Euclidean geometry, the shortest distance is not a straight line on curved surfaces, which means that light will bend when it encounters anything with mass. This is why light still bends around the moon during a solar eclipse. The moon is bending space-time, which changes the shortest distance through that portion of space. I don't know about you, but I just got goosebumps. Wow. All right. That was a lot. That's about as far as we can go without cracking open a whole can of cosmological worms, like how gravitational time dilation causes light to change frequencies, and therefore color, or gravity waves, changing the physical dimensions of objects. I'm getting carried away. But since we are here, I want to finish by talking about one teensy little thing. What happens when something gets very massive and very dense? A singular point at which a massive amount of mass exists. Schwarzschild figured this out from Einstein's equations and determined a radius, an event horizon at which something so dense would bend space-time so far that not even light could escape. He predicted a black hole. And if light can escape, that would mean you would have to go faster than the speed of light to escape the pull of a black hole, which is impossible, right? We'll find out the answer to that another time. Or at least, another time, relatively. If you like what you heard here and want to learn more, the content of this episode comes in part from the OpenStax textbooks University Physics 3, as well as other sources which you can find out more about in the description. If you would like to view a transcript or want to cite this episode, that information is also in the description. Entuition is an independent project currently run only by myself, so if you want to hear more, please share this with your friends and family. Your support is invaluable. That means valuable, by the way.